So I think I'm going to show pictures even before we do the math on this. We're going to be doing a volume by cross sections. Let's start with that. I like to look at pictures. So we're going to build a 3D. Ooh, there's a good one. And sometimes this is one of the projects. Let's see, how do I full screen that? Here we go. So you'll have a base determined by, let's see if we can get the full picture here. There we go. So look at this top, let's look at all of them. All of them have the same base. Y equals x squared is the base of the picture. And then building out of the picture, so making a 3D figure, this, excuse me, this purple one has squares built out of it. What shape do you see built out of the green ones here? Semicircles. What shape is built out of the yellow ones? Triangles. It's hard to tell if those are like equilateral or right triangles, or it's kind of hard to tell. And the blue ones look like rectangles, but not squares. So what we're going to do today is find the volume of these type of things. But how we're going to do it is basically add up the squares, or add up the semicircles, or add up the rectangles. So like yesterday, or how we normally do area, is by, let's just pick a, let's say we want the area under y equals x squared. So we want the area under y equals x squared from 0 to 1. Well, that would be the integral from 0 to 1 dx of x squared. And the reason is x squared is the height of each little piece. Of any one little piece, the height is x squared. And so we add up all the x squareds. In fact, I don't know that I've said this before, but this integration symbol, it is basically a morphed s. That's where it comes from. For some. Whoa, mind blown. I think I taught calculus for a number of years before I figured that out, or someone told me that. Like, it's the integration symbol, the antiderivative symbol, but it comes from an s, meaning sum up all of the heights. And remember, dx is the width. So we add up all those little bitty rectangles in there to get the area. So we add up all the little rectangles to make an area. Well, we're going to do that same kind of thing with cross sections today. Volumes by cross sections. Once we get going, most students find this not easy, but it's pretty straightforward, they feel like. Alright, so example 1, we're just going to jump in and learn one on the fly here. Start with the base. X squared plus y squared equals 16. Boy, it'd be nice if we knew what shape that made. What's that? What shape is it? A circle. With radius of 4. Circle with radius 4. If we needed to solve for y, which actually we will soon enough, move the x squared over, take the square root. Now we're going to do two separate problems with that base. We're going to start by saying let's find the volume if the cross sections are squares perpendicular to the x-axis. Okay, well, first I'm going to try to draw it. Then we'll see if we can Google a picture that's already out there somewhere. And then we'll actually work the problem. So drawing it's the fun part. So squares perpendicular to the x-axis. So I somehow have to draw a square like coming up out of the page. So my circle is flat on the page. That square is a 3D coming up out of the page. There's a smaller one on the left end. So kind of hard to visualize, kind of hard to draw. I know there's a picture of this out there on the internet because I found it earlier. So we want volume by cross section, base, circle. Let's see what happens. There's one right there. Oops, where did the picture go? Alright, well, we'll back up and just look at the picture that's right here. Alright, so you can see that the base is a circle, and you can see that the 3D coming out of the page are squares. Does that picture help visualize what's going on? That's the same one, although that's a lot smoother, so it's hard to tell that those are squares. Right, this one's easier to see that those are squares. They're sort of similar to our drawing. He's got his XY axis a little bit flatter, so his circle looks like an ellipse, but that's because he's got a perspective look on it. You can see what else can be done here. There's some triangles drawn. Let's see. I'm just going to leave that picture there because we're going to do semicircles next. So the base is a circle, and each cross section is a square. All right, so back to notes here. So what we want to do is add all the volumes. And we're going to say each square. How thick is each square, do you think? That's the x-axis and that's the y-axis. How thick is each square? Really thin. And how thin is really thin when we want to say the thickness of a rectangle is dx. So the thickness of each of these slices is going to be dx. Right, add all the volumes. So we want to sum the volumes. We're going to morph from English into math on the fly here. So sum the volumes means integrate. We want to sum the volumes. How about the limits? What do you think? From what to what? -4 to 4. So we're going to add up all the squares from -4 to 4. What's the area of a square? Length times width. And how about more specific to a square? Yeah, side squared. Where this is S. negative 4 to 4. S squared is the area of the square, and dx is the thickness of the square, or of the, I guess it's not a square, it's a 3D piece. So we want the integral from negative 4 to 4 of s squared, adding up all the squares that have a thickness of dx. Now this doesn't really work yet because I can't integrate s squared if I'm doing it with respect to dx. So I need to come up with some relationship between s and x. So back to our picture. Y equals square root of 16 minus x squared. That distance would be right there. So that's not the whole side length, right? That's only the top half of it. So how are s and y related to each other? S is double y. Yep. Does that make sense? One person said it, but I need more people to see it. Emma? This height is a y height? Yeah. But S is like the whole length. Like if I want the side right there, it would be the whole length of the diameter. Y is only the radius. Is another way to say it. Well, that's not the best way to say it either. Y goes from the 0 to the top of the curve. That's Y. Okay. But we need the whole side length, so we need to double Y. Mark?
Oh, okay. But S looks shorter than Y, with where it is on the circle.
Well, so it depends where you're at. So S and Y are both changing. Okay. Right? So right here, if we only look at that little piece, S is that red stripe all the way down, and Y is the green stripe. Okay. Now you're right, if we come over here, well again, Y is shorter than S. Y is half as much as S. Okay. Y is always half of S, or maybe better said, S is twice Y. And Y, we solved for Y already, is the square root of 16 minus x squared. Lots of variables going on today. So S, zoom out so we can see it all at once. An equation for S, or a length of S, is 2 times Y, but Y is the square root, so 2 times all of this. So I'm going to put all of that in for S. So negative 4 to 4, and then S is 2 square root 16 minus x squared, and then we still have dx on there. Okay, so there's a lot of pieces to this. First is understanding what the picture looks like. Second is understanding that we're going to add up all the volumes. And then next is, well, how do we get an equation for those volumes that we can actually do something with? Meaning, I want an equation that has x in it so that I can do my dx slices. What do you think the next step is? The next step is good news. I don't have to use substitution. I don't even have to, like, I could clean this up a little bit, but calculator, right? I could square all of that and it would make it nicer, but who cares? I'm going to the calculator. So rather than risk messing up the algebra, Math 9, negative 4 to 4. I need to be super careful with parentheses here. 2 square root 16 minus x squared. Make sure I'm squaring the right thing here. Dx. And then let the calculator figure it out from there. 141.333. Yes, no, eh. Let's do the same base, this time with semicircle cross sections. Same base, circle, radius 4. But now we're going to have semicircle cross sections. So this is kind of hard to draw as well. So I have semicircles coming up out of the page at me. Let's go back and look at that picture because I think we had one of those. There we go, this picture right here. It's a circle base with semicircle cross sections. Even on the x-axis, I feel like that picture needs to be like twisted around, but turn your head or turn the picture or turn the computer, and you would see the semicircle cross sections. There's another one. Semicircle cross sections. We just did the square cross sections. You can also see what's coming next. So let's add up all of the semicircles. Let's back up a little bit. X squared plus y squared equals 16. So y is the square root of 16 minus x squared. But again, that y is only the top half. And actually that might be good news for this one. So I usually start these with like word problems. I want to sum the semicircles. Sum the semicircle volumes. So sum, my S morphs into the calculus S. I'll add all the semicircles from -4 to 4. Those are x values, so I will be taking x slices. I have slices along the x-axis. And so the volume of each semicircle, see if I can draw this. Well, its thickness is dx, so I just need the area of the semicircle times dx. Because dx will be the thickness. Okay, so area of a semicircle is 1/2 pi r squared. So -4 to 4, 1/2 pi r squared dx. But I can't type that in the calculator because I can't have r's in the integrand if I'm doing a dx problem. So I need to come up with some expression for r. So look in my picture. There's r. What does r equal based on looking at the picture? Y. Good. R equals y. So we're getting closer. But what does y equal? Because I can't have r in there. I also can't have y in there. I need stuff with x in there. 16 minus square root of 16 minus x squared. Correct. I want the radius of all the semicircles, not the radius of the big circle. Integral from -4 to 4. The 1/2 pi can go out front of the integrand, or it can stay in there. It doesn't really matter, especially since the calculator is going to do the work anyway. 1/2 pi Square root of 16 minus x squared squared. There's some obvious algebra. If you want to simplify, the square and the square root cancel each other out. So that one might be worth doing just because it makes your calculator life a little easier. Pi over 2 times, so I'm going to slide the pi over 2 out front. Math 9, negative 4 to 4. I'm going to do the square root, or squaring the square root, because that saves me a little time, and that's an easy algebra step to do. If you don't like it, that's fine. You can leave it in there. $134.041. Add up the semicircles. All right, let's see if we can do one more. The base is formed by y equals x squared, y equals 0, and x equals 1. Y equals x squared, y equals 0, and x equals 1. So there's my base. And I want to form a solid with equilateral triangles as cross sections. So coming up out of the page are equilateral triangles. Again, we're short on time, so I'm not going to find that picture, but I bet if you Googled all of that, you'd probably find the exact problem in there somewhere. Or even just solid with equilateral triangle cross sections, you'd see what was going on. So I want to sum the triangles. Again, I start with an English sentence and turn it into a math sentence. So sum from what to what? What will my limits be? 0 to 1. And that means it would be dx because I'm taking x slices. And I want to add up all of the area of those triangles. So here's what you probably don't remember. Probably because you've never been taught it. Maybe you have somewhere. The area of an equilateral triangle? Root 3 over 4 times s squared. So 0 to 1, root 3 over 4, s squared, which is fine, except that I can't really integrate s and dx. So I need some expression for s. Like, what does s equal in the picture? It's this side. Well, I guess it's all the sides, but it's this side is the side I care about. What dimension is that in the picture? I was going to back up one, but you're right. It's y, but I still can't use y in this. So Connor didn't make it the next step. They told us that y is x squared. So the integral from 0 to 1, root 3 over 4 of x squared squared is our answer. And it's not very big. All right, you can omit number 10 and all the part C's. That'll make sense when you see the worksheet. Omit number 10 and all the part C's.